Hello, and welcome to Space Historians. I'm glad you've joined me tonight, ready to slow down, breathe deeply, and let your thoughts drift weightlessly beyond our world. This is your moment to leave the noise of the day behind, to step away from screens and deadlines and the relentless rush of now, and step quietly into the vast, starlit corridors of cosmic history, where time stretches back not thousands of years but billions, where the story isn't written in clay tablets or stone monuments, but in the light of distant galaxies still travelling toward us across the void. Tonight, we're going to explore a question that sounds simple at first. What is the largest thing in the universe? It's the kind of question a child might ask, pointing up at the night sky, wondering where it all ends. But the deeper you look, the more that question opens into layers of mystery, each answer revealing something larger still, each discovery pushing the boundaries of what we thought immense could mean. We'll begin with the familiar, with mountains and oceans, the giants of Earth that once defined our sense of scale. Then we'll move outward, stepping from planets to stars, from stars to galaxies, from galaxies to clusters and beyond, each leap stretching our imagination farther than the last. Along the way, we'll see how the universe organizes itself into patterns of breathtaking beauty, webs of light separated by vast gulfs of darkness, structures so immense that even galaxies become details in a grander design. If you enjoy these quiet journeys beyond our world, a like and subscribe help keep this channel orbiting. But for now, you don't need to do anything but listen. When we talk about size, it always begins with ourselves. We are the measuring stick we carry unconsciously through the world. Our sense of big and small is built from the body we inhabit, from the length of an arm, the height of a doorway, the time it takes to walk across a field. Before telescopes and satellites and scientific notation, people judged the world by what they could hold, climb, or cross on foot. For most of history, the largest things anyone could imagine were the tallest mountains, the deepest caves, the longest journeys across land and sea. Those felt immeasurable because they pushed against the limits of human endurance. Crossing an ocean without maps or engines, climbing a mountain with nothing but lungs and legs, these were the scales of large for generations. It's fascinating to notice how language itself reflects this. Words for size often come from the body. A foot was literally a foot. A yard was the length from nose to outstretched fingertip. Even ancient myths used giants to personify what was bigger than human comprehension. Something larger than life was pictured as something like us, only scaled up, taller, stronger, stretching beyond the ordinary frame of a person. The human form itself was the original measuring stick, the template against which all other sizes were compared. As civilizations grew, so did their tools for reckoning size. Builders of cities began to think in terms of spans and cubits, measures tied to elbows, hands, and strides. The Egyptians carved stones into pyramids, whose scale astonishes us even now, not only because they are tall, but because they dwarf human effort. To imagine people lifting those blocks without cranes or engines stretches our imagination backward across millennia. For them, building large was a way to brush against eternity, to make human presence endure against the backdrop of time. Size became a way to express power, permanence, and sometimes devotion. But the human sense of scale didn't stay fixed at monuments and mountains. With ships that crossed oceans, suddenly the globe itself entered human awareness as something measurable. The Earth, once imagined as endless or infinite, could be circled. Magellan's voyage in the early 1500s made it clear that you could start in one place, keep travelling, and eventually arrive back where you began. The world was vast, but not boundless. Its size could be mapped, charted, and even compared to human travel time. That was a turning point. Once you realise the Earth is a finite sphere, the next question naturally follows. What else is there, and how big could it be? We still measure size in terms of human effort even today, though we often don't notice it. A road trip is measured in hours of driving. A flight across the Atlantic is measured in meals and naps taken on the plane. Even space travel, the most extreme example we have, is described in time. It takes about 3 days to get to the moon. A rover takes several months to reach Mars. We anchor size to duration because time is something we feel directly. While kilometers in the millions or billions are hard to picture, a meter is easy. You can stretch your arms and imagine it. A kilometer is harder, but you can still walk it. 1,000,000 kilometers, that slips free from instinct. We turn to metaphors, comparisons, analogies. 20 times the Earth's circumference. About the distance light travels in a few seconds. Our sense of the immense always loops back to scales we know. This is where science gave us a new kind of measuring stick, numbers that go beyond human instinct. The invention of precise units, the meter, the second, the kilogram, allowed us to count and compare with accuracy, not just feeling. But then came something else, the need to handle numbers so large that ordinary counting systems broke under their weight. Scientific notation was born, a way of saying not just 10,000 or 100,000, but 10 to the power of 6, 10 to the power of 9, 10 to the power of 12. Each step up felt like walking away from human intuition because the brain can picture a handful, maybe a dozen, even 100 with effort. 1,000 already pushes it, 1,000,000,000 becomes abstraction, and yet the universe demands those numbers because its scale doesn't pause for our comfort. Think about how children learn big numbers. At first they count on fingers, then they count objects in a room. Soon they're told there are 100 candies in a jar, 1,000 people in a school, 1,000,000 stars in the sky. Beyond that, numbers become more like names than experiences. 1,000,000,000, 1,000,000,000,000, 1,000,000,000,000. We say the words, but few people can honestly picture what they mean. This isn't a failure of imagination. It's simply that the human brain evolved to deal with the immediate environment, with tools, with food, with distances you could cross in a day. The cosmos didn't design us to comprehend galaxies. We had to invent methods, notation, logarithmic scales, comparisons to light speed, just to try to fit the enormity of things into sentences we could say out loud. And yet, even when we use math, we still anchor it in what we know. Consider light years. It sounds simple now. The distance light travels in a year, but light moves at about 300,000 kilometers every second. In 1 second, it could go around Earth more than 7 times. In a year, it covers nearly 10 trillion kilometers. To say a star is 4 light years away, like Proxima Centauri, means it's almost 40 trillion kilometers distant. We can't imagine that number directly, so we reach for metaphors again. If you drove to Proxima Centauri at highway speeds, it would take you more than 50 million years. We bring it back to travel time, to journeys, because that's how our sense of large first formed. The funny thing is, the very act of asking, what is the largest thing, is itself a very human move. Other creatures don't seem to care about comparative size beyond survival. A bird needs to know if a branch is wide enough to hold it. A predator needs to know if its prey is bigger or smaller than itself. But humans go further. We wonder what's the biggest tree in the forest, the tallest mountain on the continent, the largest whale in the sea. We seem wired to search for limits, to test the edges of the possible. It's as if measuring size helps us anchor ourselves, to know where we fit. If we know what is biggest, we can place ourselves in the hierarchy of scale, even if we are far down the ladder. When we think of things that are truly vast, our minds often return first to the features of Earth itself. Before telescopes, before photographs from space, before we had any sense of stars being suns or galaxies being families of stars, the greatest comparisons were right here on our planet. Mountains that scraped the sky, oceans that stretched further than the eye could see. These were the giants that defined scale long before we imagined galaxies. And even now, when we talk about immensity, it helps to begin with them because they remain the first experience most of us have with the idea of nature being overwhelmingly large. Mountains have always been markers of awe. Stand at the base of one and you feel how small your body is in comparison. The air shifts as you climb. The weather at the summit can be entirely different from the weather at the foothills. Peaks carry snow when valleys are warm. They create rivers by trapping clouds, squeezing out rain, sending streams down to the plains. Mountains are not just tall piles of rock. They're engines of climate, regulators of water, makers of habitats that stretch from forests to glaciers in a single vertical span. To someone who has never seen one, a mountain is almost hard to believe. It rises in front of you like a wall, and yet it can be crossed if you're patient enough to climb. Take Mount Everest, the highest peak above sea level. Nearly 9 kilometers tall, it pushes human endurance to its limit. The air near the summit holds only about a third of the oxygen available at sea level. Every step feels heavy, every breath shallow. People who climb it bring bottles of compressed air to survive. From a human perspective, Everest is not just a mountain. It is an environment so extreme it barely allows life. And yet, in the grand scheme of Earth, Everest is only a wrinkle. If you shrank the planet to the size of a billiard ball, its highest mountains and deepest trenches would be barely noticeable to the touch. The Earth's diameter is about 12,700 kilometers. Everest is less than 9. On that scale, the tallest peak is nothing more than a scratch. This comparison is one of the first lessons in understanding scale. What feels impossibly large up close becomes tiny when set against the whole. Everest is enormous to us because our bodies are small, but to the Earth itself it is almost invisible. And this is not just true for mountains. The same lesson emerges when we look at the oceans. The Pacific is the largest single feature on our planet's surface. Covering more than 160 million square kilometers, it holds more water than all the other oceans combined. To sail across it takes weeks, even with modern ships. To fly across it takes many hours. For most of history it was an unknown immensity, a blank expanse on maps. Entire cultures lived their lives without ever seeing its far shore. To stand on a beach and look out at the Pacific is to feel the idea of endlessness pressing in. The horizon is always the same distance away, no matter how far you travel, so it seems as if the ocean could continue forever. But like mountains, oceans too can be placed in context. The Pacific has an average depth of about 4 kilometers, and in its deepest trench, the Mariana Trench, it plunges nearly 11 kilometers down. That is deeper than Everest is tall. If you drop the mountain into the trench, its peak would still sit more than a kilometer underwater. To imagine that much vertical space filled with darkness and pressure is unsettling. At those depths, the pressure is over 1,000 times greater than at sea level, enough to crush ordinary submarines. And yet, even here, life exists, adapted to a world without sunlight. The giants of Earth are not only tall or wide, they're also deep, pushing into environments where humans can barely survive. Mountains and oceans are often placed side by side in myths and stories because they represent opposites. One reaches toward the sky, the other sinks into hidden depths. One can be seen from a distance, the other conceals its immensity beneath a flat surface. But both serve the same role in our imagination. They remind us that our sense of size is always relative. A mountain may tower over a climber, but from space it looks like a ridge. An ocean may feel infinite to a sailor, but from orbit it is a patch of blue against a globe. The lesson is that immensity is not absolute. It depends on perspective, on what you compare it to. It's worth pausing to imagine what it must have been like for the first people who reached the summit of Everest. In 1953, Edmund Hillary and Tenzing Norgay stood at the highest point on Earth. For a brief moment, no other human had ever been higher while standing on solid ground. The view stretched for hundreds of kilometers across other peaks that themselves were taller than anything on other continents. And yet, above them, the sky stretched on infinitely. Even at the highest point, they were only a third of the way to where commercial airplanes now cruise. Beyond that, space begins, and beyond space, the stars. The highest mountain still leaves us close to the ground. Now picture the first explorers to cross the Pacific. Polynesian navigators steered their canoes across thousands of kilometers, using stars, winds, and currents. They set out without seeing land ahead, trusting knowledge passed down through generations. To them, the ocean was not just large, it was a living map, a field of motion and pattern. For months they might travel without touching shore, yet still know where they were by reading the sky. The Pacific, immense as it is, was thus knowable through patience and skill. Even the largest ocean could be crossed. These stories tell us something important about the human relationship to size. What we call large is not only about numbers. It is about effort, about difficulty, about what can or cannot be crossed in a lifetime. Everest feels large because it pushes the body to its limits. The Pacific feels large because it demands weeks or months of travel. Size is not just geometry, it is experience, and that is why mountains and oceans still feel enormous, even after we know their measurements. They test us, and that makes them big. But when we step back to look at Earth from a distance, their immensity shrinks. The tallest mountain is less than 1/10 of the planet's diameter. The deepest trench is even smaller in proportion. The largest ocean covers just under 1/3 of the surface. From the vantage point of space, the Earth appears smooth. Clouds, continents and seas blur together. The wrinkles that shape our sense of awe vanish into the curve of a sphere. This shift is part of the journey toward answering our question. The giants of Earth are only giants to us. They set the stage for thinking about size, but they are not ultimate limits. They are practice comparisons, stepping stones that teach us how quickly large can fade when we widen the frame. That lesson becomes even more striking when we turn from the surface to the planet as a whole. Because while mountains and oceans once defined scale for human imagination, Earth itself is not the end of the story. It's only the next comparison, a ball of rock and water that is dwarfed by what lies beyond. When we step back from the mountains and oceans that dominate the human imagination, the planet itself becomes the next comparison point. Earth is the foundation beneath our feet, the home that holds every story, every culture, every living thing we know. It feels infinite when you live upon it, wide enough to hide mysteries on its far side, large enough that most people for most of history never saw more than a tiny fraction of its surface. And yet, when you measure it, the numbers begin to reveal just how precise and limited even a world can be. Earth is about 12,742 kilometers across at the equator. That's a figure so exact that it may seem sterile at first glance, just a number. But let's try to feel it in human terms. If you were somehow able to walk in a straight line around the widest part of the Earth step by step, it would take you about 40,000 kilometers of distance to return to where you started. At a steady pace, walking 8 hours every single day, you would need well over a year to finish. That's with no oceans, no obstacles, no rest days, just walking. Even on the scale of a single lifetime, Earth is too large to fully circle on foot. That was one of the first lessons of explorers. The planet could not be measured in days or weeks of travel. It demanded months, years, sometimes generations. But compared to space, the size of Earth begins to look much smaller. The Moon orbits at a distance of about 384,000 kilometers. That's roughly 30 times Earth's diameter away. If Earth were the size of a marble, about 2 centimeters across, the Moon would be about the size of a pea orbiting 30 centimeters away. A tidy little system on a tabletop. From the scale of the cosmos, Earth is just one marble among many, and yet that marble is full of astonishing variety. Its diameter may be modest compared to what comes next, but it contains mountains, trenches, plains, deserts, rivers, forests and oceans. It contains climates from polar ice to tropical rain, and life that is adapted to every one of them. Earth's size is not just physical, it is experiential. A human lifetime is barely enough to cross its surface a handful of times, let alone to live in all its environments. Its largeness to us lies not only in its geometry, but in the richness it holds. When astronauts first left the atmosphere and looked back, they were struck by how small the Earth appeared against the backdrop of space. Photographs taken during the Apollo missions show a sphere suspended in darkness, glowing with clouds and ocean light. The blue marble image taken in 1972 became one of the most widely shared photographs in history. It gave people a perspective that had never been possible before. For the first time, the entire planet could be seen in a single frame. Every human being, every memory, every story compressed into a ball small enough to fit inside a photograph. Suddenly, the scale of Earth shifted in our imagination. It was still vast on the ground, but from space it looked fragile, finite and surprisingly tiny. That sense of smallness is amplified when you compare Earth to its neighbours. Jupiter is about 11 times wider and over 300 times more massive. Saturn, nearly as wide, has rings that stretch hundreds of thousands of kilometres. Even Neptune and Uranus, the ice giants, dwarf Earth in both diameter and volume. Compared to these giants, Earth is not especially large. In fact, among the planets of our solar system, it sits somewhere in the middle. Bigger than Mars and Mercury, smaller than the gas giants, just right to hold an atmosphere and liquid water. Its size is what makes life possible. Too small and it would not have gravity strong enough to hold air. Too large and it might have ended up like Jupiter, a swirling ball of gas. Earth's diameter is not only a measurement, it is a condition of existence. Consider also the way Earth measures against the Sun. The Sun's diameter is about 109 times that of Earth. You could line up more than 100 Earths across its face, and over 1 million Earths could fit inside its volume. From our perspective, the Sun is just a disk in the sky, something you can blot out with your thumb at arm's length. But in truth, the Sun is the colossus of our system, and Earth is a small companion circling at a safe distance. The difference in scale is difficult to internalize. We see the Sun as ordinary because it is constant, rising and setting each day. But in terms of size, it is overwhelming, and Earth is a minor detail. The scale of planets is also connected to the way we measure time. A day is the length of Earth's rotation on its axis. A year is the time it takes to orbit the Sun. These rhythms are anchored to the size and speed of our planet. Change the diameter of Earth and those rhythms would change too. A larger planet might spin more slowly, giving longer days. A smaller one might spin faster. The very scale of Earth is woven into the way we experience time itself. Every clock we build, every calendar we write, is an echo of the planet's dimensions. And then there is the question of how small Earth really is, compared to what we can imagine. The observable universe is about 93 billion light-years across. That number is almost beyond comprehension. If Earth were shrunk to the size of a grain of sand, the observable universe would still be larger than the Earth itself compared to that grain. The comparison is humbling. It shows us that even a whole planet, full of mountains, oceans, forests and cities, is a speck in a much grander scheme. But it's worth remembering that size is not the same as significance. Earth may be small, but it is where every story we know unfolds. It is the platform for thought, for life, for curiosity. When we compare it to Jupiter or the Sun, it shrinks. When we compare it to the universe, it almost disappears. Yet it is also the only place we know that holds beings capable of asking about size at all. That paradox, small in measure, vast in meaning, is part of why Earth holds such a strong place in our imagination. From the perspective of geology, Earth's size also shapes its interior. Its mass allows it to retain heat, to have a molten core that drives plate tectonics. Mountains rise and fall over millions of years because the planet is large enough to keep its interior active. Oceans exist because gravity is strong enough to hold water. Atmosphere clings to the surface because escape velocity is high enough to keep most gases from drifting away. Earth's particular diameter is not random. It is what makes Earth dynamic. It gives us weather, volcanoes, earthquakes, rivers, and the cycling of carbon and water. The size of the planet is directly tied to its character. If we turn our gaze outward, Earth is far from unique in being planet-sized. Billions of other stars are orbited by worlds of comparable scale. Some are rocky and small, others giant and gaseous. The discoveries of exoplanets over the last few decades have revealed that planets are common, perhaps the most common kind of object in the universe after stars themselves. Earth is one among countless billions, and yet, when you think about the fraction of those planets that may have just the right conditions for life, the sense of rarity returns. Its size, its distance from the sun, its balance of land and water, these details make it more than just a ball of rock. They make it a world capable of harbouring consciousness, something far rarer than size alone. When we think about the solar system, all of the planets together seem like a grand collection of worlds, each unique in its size, colour and character. And yet, as large as Jupiter is, as wide as Saturn's rings extend, the The truth is that the planets are almost incidental when compared to the central presence that holds them all in place. The Sun is not just another object in the solar system, it is the solar system. Nearly everything we see and know here is shaped by its size, its heat, and its gravity. Without it, there would be nothing. And when we begin to consider its scale, we start to realize just how small even the largest planets truly are. The Sun is about 1.4 million kilometers across. That is more than 100 times the diameter of Earth. If you lined up Earth side by side, it would take more than 100 of them to stretch across the Sun's face. In terms of volume, over 1 million Earths could fit inside. Imagine placing every mountain, every ocean, every continent, and every human being inside a hollow sun. There would still be room left over. The comparison makes Earth feel less like a planet and more like a pebble circling a bonfire. And yet, for all its immensity, the Sun looks ordinary from the ground. Day after day it appears as a bright circle in the sky, no bigger than the moon to the eye. This is because the Sun is both enormous and distant. It is about 150 million kilometers away, far enough that light itself takes 8 minutes to reach us. If the Sun were to vanish this instant, we would still see daylight for 8 more minutes before the darkness arrived. Distance disguises size. The Sun looks manageable in the sky because it is so far away, but its true scale is overwhelming. Its mass tells another part of the story. The Sun makes up more than 99% of all the mass in the solar system. Every planet, moon, asteroid, and comet combined accounts for less than 1%. In other words, almost everything here is the Sun. Jupiter, the largest planet, is immense to us, but compared to the Sun, it is only 1,000th of its mass. All of the planets together are like dust clinging to the skirts of a giant. The center is the thing that matters. Without the Sun's mass, there would be no gravity to hold the solar system together. The planets would drift off into the galaxy like seeds on the wind. The Sun is a star, and that means it is a sphere of hot plasma powered by nuclear fusion. At its core, hydrogen atoms are squeezed together under incredible pressure to form helium, releasing energy in the process. Every second, the Sun converts about 600 million tons of hydrogen into 596 million tons of helium. The missing 4 million tons are released as energy, radiating outward in the form of light and heat. That process has been going on for about 4.6 billion years, and will continue for billions more. To us, the Sun is constant, but in reality, it is a vast furnace, burning through unimaginable amounts of fuel every instant, sustaining itself through sheer scale. The light we see from the Sun began as energy deep in its core, and it took an extraordinary journey to reach us. Photons, the particles of light, bounce around inside the dense plasma for thousands, sometimes millions of years, scattering in every direction, gradually making their way outward. By the time they reach the surface and escape into space, they have been delayed and deflected countless times. The sunlight on your face today may have begun its journey long before humans even existed. Once it finally leaves the surface, it crosses the distance to Earth in 8 minutes and continues outward, some of it travelling across the galaxy, some of it reaching planets, moons, and spacecraft. The Sun is not just large in space, it is large in time, its processes stretching across scales that dwarf human history. The surface of the Sun, what we call the photosphere, is about 5,500 degrees Celsius. That is hot enough to make any known material on Earth vaporize instantly. But the outer atmosphere, the corona, is far hotter, reaching millions of degrees. The exact reason for this is still a puzzle. How can the outer layer be hotter than the surface itself? One explanation is that magnetic fields transfer energy outward in ways we don't fully understand. Whatever the cause, it reminds us that size is not just physical extent. It also includes the vastness of energy, the extremes of temperature, the reach of influence. The Sun is immense in every sense. One way to feel its scale is to consider its storms. Sunspots are regions of intense magnetic activity, cooler than the surrounding surface, but still thousands of degrees hot. Some sunspots are so large that Earth could fit inside them. Solar flares, Sudden releases of energy from the sun's surface can blast radiation across the solar system, interfering with satellites and communications. Coronal mass ejections, vast eruptions of plasma, send billions of tons of charged particles hurtling outward at millions of kilometers per hour. When these strike Earth's magnetic field, they cause auroras, shimmering curtains of light in polar skies. These are not minor disturbances. They are storms on a scale that makes hurricanes and earthquakes seem small. The sun's activity shapes space weather in the same way it shapes climate on Earth. Its storms are not only large in physical terms, but also in their reach, influencing planets millions of kilometers away. When you compare the sun to other stars, however, its size takes on a different meaning. In astronomical terms, the sun is ordinary. It is classified as a G-type main sequence star, one of the most common categories in the galaxy. There are stars far smaller, like red dwarfs, barely large enough to sustain fusion, and there are stars far larger, like red supergiants, whose diameters can be hundreds of times greater. By cosmic standards, our sun is average, maybe even modest, but for us, it is the measure of everything. Its size defines our days, our seasons, our sense of time itself. Without it, Earth would be a frozen rock in darkness. Its largeness to us is not only about its diameter or its mass. It is about its centrality, its indispensability, its presence as the anchor of all we know. The sun also shows us that size is relative to perspective. To a human being, it is enormous beyond words. To an astronomer comparing stars, it is typical. To the galaxy, it is a single point among hundreds of billions. And yet its ordinariness is what makes it valuable. An average star with a stable lifespan provides the right conditions for planets like Earth to exist. If the sun were much larger, it would burn brighter but live shorter, consuming its fuel in tens of millions of years instead of billions. That would not have left enough time for life to evolve. If it were smaller, Earth might be too cold, locked in ice. The sun's size, ordinary in cosmic terms, is extraordinary in its balance. When we stand under the night sky and look upward, every star we see is a sun. That simple truth is easy to say, but much harder to absorb. The glowing points that scatter across the dark are not sparks or lanterns hung overhead, as many once believed. They are suns, each one immense, each one blazing with energy, each one so far away that distance reduces them to dots. The sun feels unique to us because it is close, but it is only one among countless others. To understand size, we need to move outward from our familiar star and consider the wider family of stars, their variety, and their extremes. The first thing to know is that stars come in an extraordinary range of sizes. The sun is about 1.4 million kilometers across, but there are stars far smaller. Red dwarfs, the most common type of star in the universe, can be only a tenth the mass of the sun and less than half its diameter. These faint stars burn slowly, lasting for trillions of years, far longer than the sun will live. They are small by stellar standards, yet still immense compared to planets. Even the tiniest red dwarf is larger than Jupiter, and far more massive. To compare them to Earth is almost absurd. They are suns after all, even at their smallest. On the other end of the spectrum are the giants. There are stars so large that they make the sun look modest. Betelgeuse, a red supergiant in the constellation Orion, has a diameter that can stretch over 1,000 times that of the sun. If placed at the centre of our solar system, its surface would extend beyond the orbit of Mars. The idea of something that large is difficult to imagine. Picture the sun, which already dwarfs 1,000,000 Earths, then multiply its width by 1,000. That is Betelgeuse. And Betelgeuse is not even the largest star we know. There are hypergiants like VY Canis Majoris or UY Scuti, whose diameters extend even farther, to nearly 2,000 times that of the sun. If one of them replaced our star, it would swallow the orbits of Jupiter or even Saturn. These extremes show us that the sun is not exceptional in size. It sits in the middle, ordinary compared to the smallest and the largest. And that ordinariness is precisely what makes life possible here. But the existence of stars so vast, so swollen with matter and energy, stretches our sense of scale again. If Earth is small compared to the Sun, then the Sun itself is small compared to the larger stars. Each step outward pushes what we mean by largest into new territory. Stars also differ in brightness, and brightness is tied to size. Larger stars burn hotter, producing more light. And radiation. A hypergiant can shine tens of thousands of times more brightly than the Sun. But that brilliance comes at a cost. The larger a star is, the faster it consumes its fuel. While red dwarfs may live for trillions of years, a hypergiant might only survive for a few million. Size in stars is linked to lifespan. The giants are spectacular but short-lived. The small ones are faint but eternal by comparison. The Sun, once again, is balanced between extremes, lasting billions of years. Long enough for life to emerge, long enough for us to ask these questions about size at all. To appreciate the immensity of stars, it helps to think not just about their diameters, but about their energy. Every second, the Sun emits about 3.8 times 10 to the 26th watts of power. That is more energy every second than all of humanity has used in its entire history. A larger star can emit thousands of times more than that. Imagine a storm of light so intense that entire planetary systems are bathed in radiation, worlds heated and blasted by a furnace so powerful that distance is the only shield. Stars are not only large in size, they are large in output. They're engines of scale in every way. Stars also exist in systems, not just alone. Many stars are in binaries, pairs orbiting each other, or even in triples and larger groups. These systems show another kind of immensity, not the immensity of a single body, but of interaction. Stars pulling on each other with gravity, exchanging matter, sometimes colliding. The dance of such systems takes place on scales of millions of kilometers, yet is bound by the same laws that make an apple fall from a tree. Size here is not only about the star itself, but about the relationships it forms, the gravitational webs it spins. And then there are clusters, groups of thousands, or even millions of stars bound together. Globular clusters hang like lanterns around galaxies, each one a dense swarm of suns. To stand on a planet inside such a cluster would be to see hundreds of stars as bright as the moon filling the night sky. The scale of brightness, of number, of distance compressed would be unlike anything we can see from Earth. Again, stars show us that largeness is not single, but collective, not only about one, but about many together. When we talk about the immensity of stars, it is easy to lose track of the numbers. 1,000 times the Sun's diameter, 1,000,000 Earths, billions of years. These words slip quickly into abstraction, but the feeling they leave is clear. Stars push the boundary of what we call large into realms our senses cannot anchor. The night sky is filled with points of light, each one a giant beyond comprehension, some larger than our Sun, some smaller, all of them immense, and still the scale expands. For all their immensity, stars themselves are not the largest structures. They're building blocks, the way atoms are to molecules. Galaxies are made of stars, the way mountains are made, of rocks. The Sun is our giant. Other stars are giants greater still, but together they form something even larger, a collective of billions bound into a spiral, a galaxy. To move from stars to galaxies is to take another step outward, one that makes even the greatest star seem small. So from the immensity of stars, from the range of dwarves that smoulder faintly to hypergiants that blaze and die in glory, large is always relative. Even when you find a star that dwarfs the Sun, that could engulf planets whole, there is always a larger frame to place it in. When we begin comparing stars to each other, the differences can be staggering. Our Sun, which feels so overwhelming in its size and power, is in truth a middleweight, an ordinary star sitting comfortably between extremes. When stars end their lives in spectacular explosions, or when interstellar space gathers enough raw material, what emerges are some of the most beautiful and immense structures in the cosmos, nebulae. These are vast clouds of gas and dust, sometimes spread across dozens or even hundreds of light years. They are places of both death and birth, recycling matter from old stars and giving rise to new ones. If red supergiants and hypergiants are the titans of stellar life, nebulae are the cradles and graveyards, holding within them the seeds of what comes next. Their immensity is not concentrated into a single blazing sphere, but diffused, filling regions of space with luminous clouds that glow, scatter, and stretch farther than a mind can comfortably hold. The word nebula simply means cloud in Latin, and in many ways, that is what they are. But unlike clouds on Earth, which are measured in kilometers, these clouds extend for unimaginable distances. The Orion Nebula, visible to the naked eye as a faint smudge in Orion's sword, is about 24 light-years across. That means if you travelled at the speed of light, the fastest speed possible, it would take you nearly a quarter of a century to cross it. For comparison, the Sun's diameter, vast as it is only about 8 light-minutes across. The scale difference is staggering. The largest stars we know could be engulfed inside a nebula without leaving a trace visible from afar. Nebulae can be categorized by their origins and appearances. Emission nebulae glow with their own light, energized by nearby stars. Reflection nebulae shine by scattering starlight, shimmering like mist caught in a beam of light. Dark nebulae filled with dense dust block the light behind them, appearing as inky patches against the stars. Planetary nebulae, despite their name, have nothing to do with planets. They are the remnants of dying stars that have shed their outer layers, leaving behind glowing shells of gas. And supernova remnants are the spectacular leftovers of massive stars that exploded, hurling material into space with extraordinary energy. Each type has its own scale, its own role in the cycle of matter, its own version of immensity. Take the Eagle Nebula, famous for the pillars of creation captured by the Hubble Space Telescope. These towering columns of gas and dust are several light-years tall, dwarfing entire star systems. Within them, new stars are forming, their light slowly burning away the clouds that birthed them. From Earth, the image looks almost delicate, like wisps of smoke. But in truth, each pillar is larger than our solar system many times over. The seeming fragility is an illusion of distance. The reality is overwhelming size. The Crab Nebula tells a different story. In 1054, Chinese astronomers recorded a guest star that appeared in the sky, bright enough to be seen in daylight. This was a supernova, the explosion of a massive star. Today, nearly 1,000 years later, the expanding remnants form the Crab Nebula, about 11 light-years across and still growing. At its center lies a neutron star, the collapsed core of the original giant, spinning 30 times per second and beaming radiation across space. The nebula glows with energy, a reminder of both the immensity of the star that died and the immensity of the structures born from such deaths. Nebulae also hold a special place in the story of life. The elements that make up our bodies were once part of such clouds. Hydrogen and helium came from the Big Bang, but everything heavier, carbon, nitrogen, oxygen, iron, was forged in stars and spread into space by supernovae and stellar winds. Those elements gathered into nebulae, condensed into new stars surrounded by planets, eventually forming Earth. In a very real sense, we are made of nebulae. Their size is not just physical, it is ancestral. They are our origins, stretched across light years. To grasp their immensity, imagine shrinking the sun to the size of a grain of sand. On that scale, the Orion Nebula would be the size of a city. Its clouds would stretch across neighborhoods, filled with glowing dust and clusters of new grains that represent stars. The image gives us a way to bring cosmic distances into something faintly tangible. But even then, the true size remains beyond our grasp. A light year itself is nearly 10 trillion kilometers. When you say a nebula is 20 or 100 light years across, you are describing distances so great that the human mind cannot walk them, cannot travel them, can only label them. Immensity here becomes an exercise in imagination. And yet, for all their size, nebulae are fragile. They are shaped and eroded by the very stars they create. Ultraviolet radiation blasts their gas into space, carving cavities and edges. Stellar winds push and sweep the material into filaments and shells. Gravity gathers some regions into dense knots where stars ignite, while other regions disperse into the background. Over millions of years, a nebula may vanish, its gas used up or scattered. They are temporary in cosmic time. just as hypergiants are, immense, beautiful, dramatic, but fleeting. Their largeness is real, but also passing. Looking at photographs of nebulae can be misleading, though. The colours we see are often enhanced or mapped to particular wavelengths of light invisible to the human eye. The true appearance, if you could float inside one, might be dim, subtle, with stars glowing softly through veils of mist. The size, however, would be undeniable. You could travel for lifetimes and never leave the cloud. Space inside a nebula is not empty. It is filled with molecules, dust grains, atoms, all drifting in a volume larger than anything on Earth by many orders of magnitude. The immensity of nebulae also reveals something about the universe's architecture. Stars are not scattered randomly. They are born in clusters within clouds, in bursts of creation. Nebulae are nurseries, regions where gravity gathers matter into new lights. Their scale is not just in their physical extent, but in their productivity. A single nebula can form thousands of stars, each with its own system of planets, each potentially carrying the seeds of future worlds. Size here becomes generative again, the largest of a mother, holding within it countless futures. If you consider the Orion Nebula alone, it contains about 2,000 young stars in a region just a few dozen light-years wide. Each one is a sun in its own right. Each one could have planets. Each one could, in principle, host life. That single patch of sky, visible as a faint blur to the naked eye, contains more potential worlds than we could count. The scale of possibility is as large as the scale of space. And yet, as with stars, nebulae are not the largest things in the cosmos. They are immense by any measure, but they too are building blocks. They feed into galaxies, becoming part of larger structures that stretch for tens of thousands of light years. Their largeness prepares us for the next comparison, where the scale of individual stars and clouds gives way to entire collections, swarms of suns bound together into the great spirals and ellipses we call galaxies. When you look up at the night sky, some groups of stars seem to belong together. They form patterns sometimes recognized as constellations, but occasionally you find gatherings that are not just illusions of perspective. These are not stars lined up by chance from our viewpoint, but true families, clusters of suns bound by gravity, born together from the same clouds of gas and dust, moving through space as companions. They're called star clusters, and they represent another scale of immensity, not the size of one object, but the collective presence of thousands or even millions gathered into a single community. Star clusters come in two main types, open clusters and globular clusters, and both stretch the human sense of size in their own ways. Open clusters are loose associations of young stars, often only a few hundred or a few thousand in number. They are spread out across a region of space tens of light years wide, and they eventually disperse over hundreds of millions of years as their members drift away into the galaxy. Globular clusters, on the other hand, are far older and far denser. These spherical swarms can contain hundreds of thousands or even millions of stars packed tightly into a region only a few hundred light years across. Where open clusters are delicate ephemeral gatherings, globulars are ancient, enduring families that orbit galaxies like lanterns, each one older than almost anything else we can observe. The Pleiades is perhaps the most famous open cluster, visible in the northern hemisphere as a small group of bright stars often mistaken for the Little Dipper. Even without a telescope, you can see half a dozen or more. With binoculars, dozens appear. In truth, the Pleiades contains more than 1,000 stars, all born about 100 million years ago, young by stellar standards. These stars are hot and blue, shining brightly against the dark, still wrapped in wisps of the nebula that gave birth to them. From Earth, they look close together, but in space, they span about 43 light years. That distance is vast, far larger than the sun's reach, yet we see them as a compact cluster, because they remain bound, moving together through the galaxy. Their immensity lies in their collective identity, in the way they remind us that stars, like people, often begin life in groups. Globular clusters take this idea to another extreme. Consider Omega Centauri, the largest globular cluster in our galaxy. It contains an estimated 10 million stars, all crowded into a sphere about 150 light-years across. From Earth, even with the naked eye, it appears as a hazy patch of light in the southern sky. Through a telescope, it becomes a dazzling swarm, stars packed so tightly that from a planet inside it, the night sky would blaze with hundreds of bright suns, each one as luminous as our moon. Darkness as we know it would barely exist. Imagine standing on such a planet and seeing the sky filled not with constellations separated by blackness, but with a glowing sea of light in every direction. The immensity would not only be physical but visual, overwhelming in its intensity. Globular clusters are also ancient. Many are nearly as old as the universe itself, dating back more than 12 billion years. That means they formed when the cosmos was young, only a fraction of its current age. The stars within them are old, faint and red, long past their youthful blaze. In that sense, globular clusters are fossils, living archives of an earlier era. Their size is not only in their number of stars, but in their age, their persistence, their ability to endure across cosmic time. The way clusters form reveals something about scale as well. Stars are born in groups because gravity pulls the material of a nebula together in many places at once. Rarely does a single star form in isolation. Instead, a cloud fragments into knots, each collapsing into a star. Over time, those stars share momentum, orbiting a common center. Some eventually wander away while others remain bound. The result is a cluster, a family that carries the memory of its shared birth. Size here is collective, not just about the stars themselves, but about their togetherness. It's important to remember that clusters, while vast, are not static. Open clusters drift apart, their stars becoming indistinguishable from the rest of the galaxy. Globular clusters may slowly erode as gravitational tides pull them apart, but for millions or even billions of years, they remain coherent, swarms of suns travelling together. Their immensity is in their ability to resist dispersal, to remain families even as galaxies evolve around them. From Earth, looking at a cluster is humbling because it collapses the scale of space. Instead of seeing stars scattered across thousands of light years, you see them grouped into a small patch, a reminder that the cosmos is structured, organized, layered. The immensity of clusters lies in this order, in the way gravity sculpts stars into patterns we can recognize, not random, but familial. Think of the Pleiades again. Each star is massive compared to the Sun, many times brighter, many times larger, and yet together they appear like jewels sprinkled across the sky, delicate and close. The eye cannot measure their distances. The mind has to translate. Each one is separated from its neighbor by light years, vast gulfs of emptiness, and still they belong together, moving as a group, tracing a path through the Milky Way that will last for millions of years. Clusters also provide astronomers with laboratories for understanding stars. Because all the stars in a cluster formed around the same time and from the same material, their differences can be studied as differences of mass, not of age or composition. That means clusters are keys to stellar evolution, helping us understand how stars live and die. In that sense, their immensity is intellectual as well as physical. They are not only vast in number, but vast in meaning, offering insights into processes that shape the entire cosmos. And yet, like every scale we encounter, clusters themselves are not the largest. They are steps. Their swarms of stars, impressive though they are still only fragments of galaxies. Our Milky Way contains more than 150 known globular clusters, each one immense, yet each one only a satellite to a greater whole. The scale of clusters prepares us for the leap to galaxies, where billions of stars gather into vast disks and spirals, each one larger than everything we have considered so far. So, from the open gatherings like the Pleiades, from the dense spheres like Omega Centauri, from the ancient families of suns that drift together across time, the families of stars are immense, but they themselves belong to something larger. When star clusters remind us that suns can be born together and travel as families, galaxies reveal the next order of structure. If a cluster is like a village of stars, then a galaxy is a city, not of hundreds or thousands, but of billions. When we speak of galaxies in the abstract, they sound distant, almost unreal, like mathematical constructs or ideas that belong in textbooks. But we live inside one. Every star you have ever seen with the naked eye, every constellation, every cluster, every familiar point of light is part of the Milky Way. This is our galactic home, a structure so immense that we cannot see it all at once, yet so close that we are part of it. The Milky Way is both invisible and unavoidable. Invisible because from the inside, we cannot step back far enough to take a photograph of the whole. Unavoidable because everything we see above us belongs to it. Its scale is beyond what we can comprehend directly. Yet, it is also the most intimate of the great cosmic structures, the one that contains our Sun, our Earth, our history. The Milky Way is a barred spiral galaxy about 100,000 light-years across, though some estimates stretch it even larger. It contains somewhere between 100 and 400 billion stars, along with planets, nebulae, and massive reservoirs of dark matter. Its arms sweep out from a central bar-shaped core, curving across the disk like streams of light, full of young stars and glowing clouds. From our vantage point on Earth, inside one of those arms, we see the galaxy edge on. That is why the Milky Way appears as a pale band across the night sky. We are looking along the dense plane of the disk, through thousands of light-years of stars compressed into a soft shimmer. Our Sun is located about 27,000 light-years from the galactic centre, in a minor arm called the Orion Spur, between two larger arms. That position is almost suburban, far from the crowded bustle of the core, but not on the edge either. It is a place that has offered stability for billions of years, far from the dangers of the galactic centre, where radiation, black holes and supernova are far more common. Our home system orbits the centre of the galaxy once every 225 to 250 million years. That means since Earth formed, the Sun has circled the Milky Way more than a dozen times. Each orbit is a galactic year, and humanity has existed for only a fraction of one. In terms of the galaxy's lifespan, we are newborns. At the very heart of the Milky Way lies Sagittarius, a star, a supermassive black hole with about 4 million times the mass of the Sun. It is invisible directly, but its presence is revealed by the way stars orbit at incredible speeds around it. Gas and dust falling toward it emit bursts of radiation, and in rare flares, the black hole lights up as material spirals inward. This colossal object is the anchor of the galaxy, the gravitational centre around which everything else turns. Its size in terms of mass is overwhelming, but its physical diameter is tiny compared to the galaxy itself. Once again, the universe shows us paradox. The largest structures are often shaped by the smallest volumes, the most immense collections controlled by the most compact forces. The Milky Way is not uniform. Its disk is full of regions where stars are born, nurseries glowing with nebulae. Some arms blaze with hot young blue stars, while other areas are filled with older, dimmer populations. Between the arms, vast clouds of hydrogen drift, reservoirs of future stars. The halo surrounding the galaxy contains globular clusters, ancient families of suns that orbit like satellites. And beyond the visible, most of the galaxy's mass is dark matter, an invisible presence that outweighs all the stars and gas combined. Without it, the galaxy would fly apart, unable to hold its rotation together. Its immensity is not only in what we see, but in what we cannot. To imagine the Milky Way, it helps to think of it as a great disk of light. But that light is sparse. The stars are not crowded together the way they appear on maps. On average, the nearest star to the Sun, Proxima Centauri, is more than 4 light-years away. If the Sun were a ping-pong ball, the nearest star would be another ball placed over 1,000 kilometers away. Galaxies look solid in photographs, but they are mostly empty space, their immensity spread thin. This combination, billions of stars yet vast emptiness between them, defines what a galaxy really is. Immense in number, immense in reach, but delicate in density. The Milky Way also has companions, the large and small Magellanic Clouds, irregular dwarf galaxies, orbit nearby, trailing streams of gas as they are pulled by our galaxy's gravity. Other dwarfs are scattered around as well, satellites that remind us that even galaxies exist in systems. We are not isolated. The Milky Way belongs to a local group, a collection of more than 50 galaxies bound together, dominated by our spiral and the Andromeda Galaxy. This family of galaxies is small compared to clusters, but it shows that even a home as immense as the Milky Way is part of something larger. From Earth, the Milky Way has always been a source of wonder. Ancient cultures saw it as a river of milk, a path of souls, a road across the heavens. To the naked eye under dark skies, it is breathtaking, a streak of white so dense with stars that it looks like smoke. Today, light pollution hides it from most people, but for thousands of years, it was one of the most striking features of the night. It was not just a collection of stars, it was a reminder that we belong to something vast, something unmeasurable. That sense has only deepened as we've learned what it truly is. A galaxy, a city of billions, our home in the cosmos. The scale of the Milky Way is difficult to feel. Imagine reducing the galaxy to the size of North America. On that scale, the solar system would be no larger than a coin. The entire history of humanity, everything we have ever known, fits inside that coin, while the galaxy stretches from coast to coast. That image conveys not only size, but perspective. We are local creatures in a structure far too big to traverse, far too immense to fully imagine. And yet, it is ours. It is the only galaxy we can say with certainty holds life. That alone gives it a significance beyond measurement. The Milky Way is also dynamic. Stars are born and die within it every day. Gas clouds collapse, supernovae explode, black holes consume, clusters drift. Over billions of years the galaxy has changed, and over billions more it will continue to change. It will eventually merge with Andromeda, forming a new, larger galaxy. The name Milky Way may not always apply. Its identity is temporary, like everything else in the cosmos, immense but not eternal. When we try to hold the Milky Way in our minds, we inevitably fall back on metaphors, cities, disks, rivers of light, because our senses are not built for scales like this. But perhaps that is part of the beauty. The galaxy reminds us that the universe is not sized for human comfort, it is sized for itself. Our home is not small, but it is vast beyond our capacity to feel. To know that and still find a way to describe it is part of what makes science an act of wonder. For most of human history, the Milky Way was thought to be everything. The faint band of light across the night sky, the stars scattered around it, these seemed to encompass the whole cosmos. Even as telescopes improved and revealed more distant objects, many astronomers believed that what we now call galaxies were simply nebulae within our own system, clouds of gas perhaps, or clusters of stars, but not separate structures in their own right. The idea that the universe extended far beyond the Milky Way, that our galaxy was only one among countless billions, was a revelation that came surprisingly late. And when it did come, it transformed our understanding of scale more dramatically than almost any other discovery. The debate came to a head in the early 20th century. Some astronomers argued that spiral nebulae, those faint whirlpool shapes visible through telescopes, were part of the Milky Way. Others suspected they were island universes, separate galaxies far beyond our own. The question could not be settled until someone found a way to measure their distances. That breakthrough came in the 1920s, when Edwin Hubble used a type of variable star called a Cepheid to calculate the distance to the Andromeda Nebula. What he found was staggering. Andromeda was not a cloud within the Milky Way. It was a galaxy in its own right, millions of light years away, larger than our own. That single measurement expanded the universe overnight. Suddenly, the billions of stars we thought encompassed everything were only a fraction of the whole. The faint smudges scattered across the sky were not nebulae but galaxies, each one containing billions of stars, each one a separate island of light, floating in the vast ocean of space. The immensity we thought we knew multiplied beyond imagination. If the Milky Way was a city of stars, then the universe contained billions of cities, each one as vast and complex as our own. The Andromeda Galaxy is our nearest large neighbour, about 2.5 million light-years away. It is a spiral even larger than the Milky Way, with over 1 trillion stars. Through a telescope, you can see its faint glow stretching across the sky. But in truth, it spans more than 220,000 light-years. To say those numbers is easy, but to feel them is almost impossible. Imagine a civilization on a planet orbiting one of its stars. Their night sky would be filled with the glow of billions of suns, just as ours is. And just as we look toward Andromeda, they might look toward the Milky Way and wonder what lies within. The immensity is not just in distance, but in the parallel possibilities, billions of stars carrying billions of chances for worlds and stories. Galaxies come in different shapes and sizes. Spirals like the Milky Way and Andromeda are characterized by sweeping arms full of young stars and glowing nebulae. Elliptical galaxies are vast, featureless spheroids containing hundreds of billions of old stars, often lacking the gas needed for new star formation. Some of the largest known galaxies are ellipticals, swollen into enormous shapes by mergers with other galaxies. Then there are irregular galaxies, chaotic in appearance, often shaped by gravitational interactions, collisions, or distortions. Together, these varieties show that galaxies are not static objects, but dynamic, changing structures, constantly influenced by gravity, collisions, and the flow of matter. When astronomers first realized that galaxies were separate from the Milky Way, it transformed our sense of place. Before that, many believed our galaxy was the entire cosmos. The discovery that the faint smudge of Andromeda was actually another galaxy, larger than our own and millions of light-years away, expanded the universe in a way that is difficult to overstate. Galaxies multiplied, and with them the immensity of the universe itself. What we thought was everything became a fragment. Consider also the largest galaxies known, such as IC 1101, an enormous elliptical galaxy more than 6 million light-years across, containing perhaps 100 trillion stars. That number is so large it almost becomes meaningless. 100 trillion stars, each with planets, each with potential clusters and nebulae, all bound into a single galaxy. Compared to that, the Milky Way is modest, and yet IC 1101 is still only one galaxy among billions. Its immensity, overwhelming as it seems, is still a fragment of the whole. The presence of supermassive black holes at the centers of galaxies adds another layer of scale. The black hole at the center of the Milky Way, Sagittarius A star, has a mass of about 4 million suns. In larger galaxies, the central black holes can reach billions of solar masses. These are objects so dense that even light cannot escape their gravity, and yet, rather than destroying their galaxies, they seem to play a role in shaping them, influencing star formation and regulating growth. The largest structures in the universe are often bound together by the smallest volumes imaginable. Size once again reveals paradox. When you think of galaxies, it can help to imagine them as cities. Each star is like a house, each cluster like a neighborhood, each spiral arm like an avenue stretching across light years. The dark lanes of dust are like rivers or forests between districts, shaping where the stars are brightest. The analogy is imperfect, but it conveys something of the immensity. Just as cities contain countless lives, galaxies contain countless stars, each one with its own planets, its own potential. The scale of a galaxy is not just in its distance or its light years. It is in its multiplicity, in the billions of individual stories it holds. From Earth, we can see only a handful of galaxies with the naked eye. The Milky Way itself, stretched across the sky as a pale band of light, is the view from inside, our perspective on our own galaxy's disk. Andromeda is visible as a faint patch. Under very dark skies, the large and small Magellanic Clouds, two dwarf galaxies orbiting the Milky Way, can be seen in the southern hemisphere. Beyond those, most galaxies require telescopes to reveal. Yet when telescopes do reveal them, the numbers become overwhelming. The Hubble Deep Field, a photograph taken by pointing the Hubble Space Telescope at a tiny, seemingly empty patch of sky, revealed thousands of galaxies, each containing billions of stars. Multiply that across the entire sky, and the total number of galaxies in the observable universe is estimated to be in the hundreds of billions. Each one a city of billions, each one vast beyond comprehension. And yet galaxies are not the end either. They are immense, yes, but they gather into larger structures still, clusters of galaxies bound by gravity, superclusters stretching across hundreds of millions of light years, filaments forming a cosmic web that spans the universe. The immensity of galaxies prepares us for the immensity of those structures, where even billions of stars become details in a larger pattern. The discovery of island universes was not the end of the journey outward. It was only another step. Galaxies, vast as they are not static. They are not frozen pinwheels drifting serenely in space. They move, pulled by gravity, influenced by their neighbours, travelling on paths that span millions of years. And sometimes those paths intersect. When they do, the result is one of the most spectacular events in the universe, a galactic collision. The name may sound violent, as if galaxies crash together like solid objects, but the reality is stranger and more elegant. They pass through one another, their stars almost never colliding, directly because the spaces between stars are so vast. What collides are their shapes, their clouds of gas, their gravitational fields, their identities. The result is a slow-motion embrace that lasts for hundreds of millions, even billions of years, reshaping both galaxies into something new. The idea of galaxies colliding may feel counterintuitive at first. After all, each galaxy is so enormous, and space between them so vast, that it seems unlikely they would ever meet. But gravity is patient, and galaxies are constantly moving within larger structures like groups and clusters. Over cosmic time scales, encounters are inevitable. In fact, collisions are a normal part of galactic evolution. Many galaxies we see today are the result of past mergers, their shapes testaments to ancient interactions. The smooth, round forms of giant elliptical galaxies, for example, are thought to be the result of countless spirals merging over time. Our own Milky Way is on such a path. It and the Andromeda Galaxy are approaching each other at about 110 kilometers per second. That sounds impossibly fast, faster than anything we experience in daily life. But in cosmic terms, it is a gentle drift. The two galaxies are still 2.5 million light-years apart, and it will take about 4 billion years before they meet. When they do, they will begin a long dance, passing through each other, their shapes torn into streams and tails, their stars flung into new orbits, their gas clouds compressed into bursts of star formation. Over time, the two spirals will merge into a single larger elliptical galaxy, sometimes called Milkomeda. Humanity, if it still exists then, will witness night skies filled not with distant smudges, but with Andromeda looming larger and larger until the two become one. What makes these collisions so immense is not just their scale in distance, but their scale in time. They unfold over spans so long that no single observer could ever see the whole event. From the first approach to the final merger can take billions of years. A galaxy may stretch into streams, recover, pass through its partner again, and repeat this cycle before settling. What looks like a frozen image in a telescope is actually a moment in an ongoing transformation. When we see colliding galaxies in photographs, we are seeing a snapshot of a dance that began long before us and will continue long after. The antennae galaxies are one of the most famous examples. Located about 45 million light-years away, they are two spirals in the process of merging. Their stars and gas stretched into long arcs that resemble antennae. In the regions where the gas clouds collide, new stars are forming at incredible rates, turning the galaxies into a starburst factory. The collision, far from destroying them, is creating new generations of suns, perhaps new planetary systems, perhaps new places for life. Immensity here is creative as much as it is destructive. Another striking case is the Whirlpool Galaxy and its companion. The larger spiral is pulling on the smaller one, distorting its shape, drawing out streams of stars and dust. The interaction has triggered waves of star formation along the spiral arms, making them blaze with bright young clusters. Collisions are not just endings, they are beginnings, moments where the raw material of galaxies is reshaped into new structures, and while stars rarely collide, the same cannot be said for gas and dust. When massive clouds and colliding galaxies meet, they compress, collapse, and ignite in starbursts. These bursts can create thousands of stars in a short period of cosmic time, turning the galaxy into a brilliant forge. In some cases, the collision funnels material into the central black holes of the galaxies, feeding them and causing them to flare as quasars, some of the brightest objects in the universe. Collisions are not quiet. They echo across space in light and energy. It is tempting to imagine a galactic collision as catastrophic for planets, but the truth is more subtle. While stars are unlikely to collide, their orbits can change drastically. A planet like Earth circling its star might be carried into a new trajectory, its night sky forever altered as the pattern of stars shifts. Some stars may be thrown into intergalactic space, becoming wanderers unbound from any galaxy. Others may find themselves drawn into new clusters, new neighborhoods. For life on planets, the changes could be profound, though spread across spans too vast for living beings to notice directly. On the time scales of biology, a galactic collision is a slow reshaping, not an instant catastrophe. The scale of these events stretches our imagination. To describe them requires numbers that slip into abstraction, tens of thousands of light years for the structures, billions of stars involved, billions of years to unfold. And yet, when telescopes capture their images, the result is strikingly beautiful. Delicate arcs of light, streams of stars curving through darkness, spirals warped and twisted, glowing knots of new birth. Collisions, for all their immensity, create patterns that look almost like art. They are reminders that the universe's largest forces can also create the most intricate forms. Our Milky Way has already been shaped by collisions. Astronomers have identified streams of stars in its halo, remnants of smaller galaxies that were consumed in the past. The Sagittarius Dwarf galaxy, for example, is currently being torn apart, its stars stretched into streams that wrap around the Milky Way. Over billions of years, many small galaxies have merged into ours, feeding its growth. The Milky Way is not static. It is a palimpsest of past collisions, a structure built from countless smaller ones. Its immensity is layered, a record of interactions across time. When we place galaxies in this context, their size becomes more than a matter of how wide they are or how many stars they contain. Their immensity includes their histories, their futures, their transformations. A galaxy is not only a city of stars, it is a participant in cosmic relationships, bound to meet others, bound to change. To think of galaxies as solitary is to miss half their story. Their largeness lies in their connections as much as in their numbers. Galaxies themselves are immense, each one a city of billions of stars, but they are not scattered randomly through the universe. Just as stars gather into galaxies, galaxies gather into clusters, forming neighborhoods on scales that are even harder to comprehend. A galaxy cluster is a collection of dozens, hundreds, or sometimes thousands of galaxies, bound together by gravity, stretching across millions of light years. Within these structures, galaxies move like residents of a crowded metropolis, pulled by one another's gravity, interacting, colliding, reshaping, and evolving together. Our own Milky Way belongs to a small group, the Local Group, which contains a little more than 50 galaxies, including Andromeda, the Triangulum Galaxy, and many dwarfs. But the Local Group is modest compared to true clusters. A typical galaxy cluster contains many more members, packed into volumes so large that light takes millions of years to cross them. The Virgo cluster, for example, lies about 65 million light-years away and contains more than 1,000 galaxies. To imagine that number, think of a night sky filled with not stars but entire galaxies, each one holding billions of stars of its own. That is the scale of a cluster. Galaxies themselves become points of light the way stars appear to us. The immensity of these neighborhoods is not only in their numbers, it is also in the space between. Galaxies within a cluster may be separated by millions of light years, yet compared to the emptiness between clusters, they are still crowded. Gravity holds them together, and dark matter plays a crucial role. In fact, most of the mass of a cluster is not in its stars or even its gas. but in dark matter, the invisible substance that outweighs everything we can see. Without it, clusters could not hold together. Their galaxies would drift apart. Dark matter's unseen immensity defines the very structure of these neighborhoods. One of the most striking features of galaxy clusters is the hot gas that fills the space between galaxies. This gas is so thin that in any small volume it would seem like a vacuum, but stretched across the vastness of a cluster, it becomes significant. Heated to tens of millions of degrees, it glows in X-rays, visible only to special telescopes. In fact, the mass of this gas often exceeds the mass of the galaxies themselves. A galaxy cluster is not empty between its members. It is filled with a medium of extraordinary scale, hot and diffuse, invisible to human eyes, but immense in its presence. The Coma cluster is another example. About 330 million light-years away, it contains thousands of galaxies. In images, it looks like a swarm. Each bright point a galaxy. Each galaxy a collection of billions of stars. The sheer number is dizzying. It is like looking at an ocean made of galaxies, each wave a cluster of suns. The immensity here is not only physical, but numerical. We are dealing with counts so large that even the most patient imagination begins to falter. Collisions so dramatic at the galactic scale are common in clusters. Galaxies move under mutual gravity, and their paths cross often. The result is constant change, mergers, distortions, bursts of star formation. Over billions of years, spirals may merge into ellipticals, and clusters themselves evolve. But even the clusters are not eternal. They are dynamic, shifting, reshaping, their galaxies in motion, their gas radiating, their dark matter halos binding it all. Clusters can also reveal the presence of dark matter in another way, through gravitational lensing. The gravity of a massive cluster can bend light from more distant galaxies, distorting their images into arcs and smears. By studying these distortions, astronomers can map the distribution of mass within the cluster, much of it invisible. In this way, clusters are natural telescopes, amplifying the universe behind them. Their immensity is not only in their size, but in their ability to bend the very fabric of space. The scale of time also plays a role. Clusters form over billions of years as smaller groups of galaxies merge. They are still forming today. The universe is full of these neighborhoods in various stages of growth, some compact and dense, others loose and sprawling. The largest clusters can stretch 10 million light-years across, containing thousands of galaxies. On that scale, even a structure as vast as the Milky Way is just a detail, one among many, like a single building in a city skyline. It is humbling to realize that what we see as the largest things in our daily perspective, planets, stars, even the sun, are lost entirely within a cluster. Earth, the solar system, even the galaxy, are points within points, layers within layers, each scale subsumed into the next. A cluster is not simply large, it redefines what large means, forcing us to recalibrate our sense of proportion. And yet, as always, clusters are not the end. They themselves gather into superclusters, even larger structures that span hundreds of millions of light-years. Our local group, modest as it is, belongs to the Virgo supercluster, which in turn is part of an even greater structure called Laniakea. Immensity never stops expanding. Clusters are immense, but they point us outward still, toward webs of galaxies that connect across the observable universe. When you step back to see clusters as they truly are, you begin to notice that the universe is organized. It is not a random scattering of lights, but a hierarchy of structures, each nested within the next. Stars form galaxies. Galaxies form clusters. Clusters form superclusters. And superclusters trace the largest patterns we know, the cosmic web itself. The immensity of clusters is a stepping stone, a middle rung on the ladder of scale that reaches from planets to the edge of what we can observe. The largest clusters are among the most massive structures bound by gravity in the entire universe. They contain the combined mass of thousands of galaxies, quadrillions of stars, all held together by forces we cannot see but can measure by their effects. To stand at the edge of such a cluster, if such a thing were possible, would be to see a sky dominated not by individual stars but by entire galaxies. a cityscape of lights, each one a world of billions. The immensity would be visual, overwhelming, a reminder that the universe builds not only in size but in layers, each one vaster than the last. From the local group to the Virgo cluster, from hundreds of galaxies to thousands, the scale expands, and with each expansion, our sense of home shifts. We are not just citizens of Earth or even of the Milky Way. We belong to a cluster, a neighborhood, a region of space defined by the collective gravity of galaxies. The immensity of clusters is not distant. It is the context in which our galaxy exists, the framework that holds us in place. And beyond that framework lies something larger still. When galaxies gather into clusters, the scale already feels overwhelming. Thousands of galaxies, each one a city of billions of stars, orbiting together under gravity. But even these clusters are not isolated. They too belong to something larger. Just as stars form galaxies and galaxies form clusters, clusters themselves link into still greater structures called superclusters. These are the webs of the cosmos, patterns that stretch across hundreds of millions of light years, immense enough to begin revealing the architecture of the universe itself. Our own Milky Way, with its billions of stars, is part of the local group. The local group belongs to the Virgo cluster, and the Virgo cluster is part of the Virgo supercluster, which spans about 110 million light-years. For a long time, astronomers thought of the Virgo supercluster as our home in the large-scale structure of the universe. But more recent research revealed that even Virgo is not the final word. It is only one part of something even greater, a supercluster called Laniakea. The name means immense heaven in Hawaiian, and it stretches across more than 500 million light-years, containing about 100,000 galaxies. To imagine such a thing is almost impossible. It is like trying to picture every city, every town, every home on Earth all at once, then multiplying that vision until it covers distances larger than the mind can hold. Superclusters are not simple blobs of galaxies. They are shaped by gravity into filaments and walls, great strands of galaxies connected across cosmic voids. When astronomers map them, the universe begins to look like a web, with threads of light connecting nodes of density. Between the threads are vast empty regions, voids where few galaxies exist. This cosmic web is the largest pattern we know, the scaffolding upon which the universe is built. The immensity of superclusters lies not only in their size, but in their role as the framework of everything. To understand the scale, consider that light travels about 9.5 trillion kilometers in a year. A supercluster can be 500 million light-years across. That means light moving at the fastest speed possible would take 500 million years to cross from one side to the other. Entire species could evolve and vanish in the time it would take a single beam of light to make the journey. Compared to such distances, everything we experience is instantaneous, fleeting. The size of superclusters stretches time as much as it stretches space. The shapes of these webs are revealed through surveys that chart the positions of galaxies. When plotted, the universe does not look random. It looks like foam, with bubbles of empty space surrounded by filaments of galaxies. The Sloan Digital Sky Survey and other mapping projects have shown us these structures in remarkable detail. Superclusters like the Sloan Great Wall, which spans 1.4 billion light-years, are some of the largest known. These are not objects in the traditional sense. They are patterns of galaxies, flows of matter, gravitational rivers shaping the cosmos. Their immensity is structural, architectural, the way beams and arches define a building. Our place within this web is humbling. The local group, the Virgo cluster, the Virgo supercluster, Laniakea. These are layers of belonging that expand outward, each one dwarfing the last. To think that our entire galaxy, with its 100,000 light-years of stars, is only a minor detail in a thread of a supercluster is to realize how far size has taken us from our starting point. What once felt large, mountains, oceans, planets, is lost within galaxies. What once felt infinite, galaxies themselves, becomes details within webs. The ladder of scale stretches without end, and each step redefines the word large. Superclusters are not static. They too are evolving. Shaped by gravity and expansion, galaxies fall along filaments, drawn into clusters, clusters drawn into larger structures. Over billions of years, the cosmic web has grown, its strands stretching as the universe expands. Yet gravity slows the expansion locally, pulling matter into denser regions, shaping the walls and filaments. The result is a balance between growth and clustering, expansion and attraction, the interplay that gives the universe its texture. The immensity of superclusters also raises questions. Are they the largest things in the universe, or are they themselves part of something larger? Some researchers have suggested that superclusters connect into even greater filaments, structures that might span billions of light years. But here we begin to approach the limits of observation. Beyond a certain scale, the expansion of the universe itself blurs the picture. Distances stretch faster than light can cross them, and galaxies slip beyond the horizon of what we can see. The largest structures we map may not be the largest structures that exist. Immensity here becomes not only a matter of scale, but of knowledge, a horizon beyond which we cannot yet peer. And yet, even within the observable, the webs of galaxies already reveal a grandeur beyond anything in our daily lives. Imagine shrinking the Milky Way to the size of a grain of sand. On that scale, the Virgo supercluster would still stretch hundreds of kilometers, a vast web of glowing grains connected by threads. The immensity of scale becomes almost tangible in metaphor, even if the true numbers remain beyond comprehension. Superclusters also remind us that the universe is not uniform. It is not the same everywhere at every scale. There are places of density where galaxies swarm, and places of emptiness where little exists. The cosmic web is a tapestry of contrasts, vast structures side by side with vast voids. The immensity is not just in the things that are there, but in the spaces between, the gulfs that stretch across millions of light years. When we step back far enough to see these webs, galaxies cease to look like individuals. They become dots, threads, textures in a larger whole. The perspective shifts. Immensity is no longer about the size of one object, but about the patterns that emerge when many objects interact. A supercluster is a relationship as much as a thing, a vast arrangement of galaxies drawn into order by the invisible hand of gravity. And as with every step we've taken, superclusters are not the final word. They are immense, yes, but they themselves belong to an even larger pattern, the entire observable universe, stretching across nearly 93 billion light years. The webs of galaxies fill that space, but beyond them lies the greatest immensity of all, the cosmos itself. When astronomers began to map galaxies in 3 dimensions, the picture that emerged was not one of randomness. It was not a scattering of lights across an empty void, nor a uniform mist of stars smeared evenly through space. Instead, the maps revealed a pattern, an intricate network of threads and nodes, filaments of galaxies stretching across hundreds of millions of light years, intersecting at dense regions where clusters and superclusters reside, with vast voids in between. This structure is called the cosmic web, and it is the largest arrangement of matter that we know. To look at it, even as a diagram, is to see the architecture of the universe on its grandest scale. The cosmic web is made of filaments, immense strands of galaxies and dark matter that trace paths like highways across the cosmos. Where filaments meet, clusters of galaxies form, dense intersections glowing with billions of stars. Between the filaments are enormous voids, regions of near nothingness, sometimes hundreds of millions of light years across, containing only a few galaxies or none at all. The contrast is striking, strands of matter stretching endlessly, separated by expanses of emptiness. Together they form a pattern that looks almost organic, like the branching of neurons in a brain, or the threads of a spider's web. The largest structure in the universe resembles things we see on the smallest scales, a reminder that patterns echo across levels of reality. The size of these filaments defies ordinary comprehension. A single filament can span 500 million light years. Within it are hundreds of thousands of galaxies, each galaxy containing billions of stars. The light from one end would take 500 million years to reach the other. To give a sense of proportion, when the dinosaurs roamed Earth, Light that is only now reaching us may have been leaving galaxies on the far side of such a filament. Immensity here is not only distance but time, stretching across ages far beyond human history. One of the largest known structures is the Hercules Corona Borealis Great Wall, a filamentary supercluster complex over 10 billion light-years away. It is estimated to be about 10 billion light-years in length, making it the largest single structure ever identified. That distance is so great that the light from it has been travelling toward us for most of the history of the universe itself. We see it not as it is now, but as it was billions of years ago. Even calling it a structure can feel misleading, because on such scales the universe itself is expanding, and the thing we name may already have stretched or changed beyond recognition. Yet, it stands as a marker of immensity, one of the farthest reaches of size that we can describe. The cosmic web forms because matter was not distributed evenly in the early universe. Tiny fluctuations in density after the Big Bang grew over billions of years as gravity pulled matter into slightly denser regions, which in turn attracted more matter, amplifying the pattern. Dark matter, invisible but abundant, played a key role, creating gravitational scaffolds upon which gas and galaxies gathered. The filaments we see today are the result of that process, threads drawn out of initial ripples magnified into cosmic highways of structure. The web is not just arrangement, it is history, written across billions of years. Dark matter itself remains unseen, but its effects are everywhere. Simulations of the universe, starting from the physics of the Big Bang and the laws of gravity, recreate the cosmic web with stunning accuracy. When you compare the maps of real galaxies to the simulated patterns of dark matter, they match. The web is not an accident. It is the natural outcome of physics acting on scales so large that galaxies themselves become mere details in the pattern. The immensity of the web is not only its size, but its inevitability. What is striking about the cosmic web is that it gives the universe texture. Instead of being a bland expanse, it is a tapestry of density and emptiness, light and darkness, filaments and voids. If you could somehow step outside and look back, you would see it stretched like lace, glowing threads across a black background. Galaxies would no longer be the focus. They would be beads on the strings, ornaments on the filaments, details in a far larger design. The immensity is not in the galaxies themselves, but in their arrangement, in the way they trace invisible scaffolds of matter and gravity. Voids are as important as filaments. These vast, empty spaces make up most of the universe, regions where galaxies are sparse or absent. A void can be 300 million light-years across, a bubble of near nothingness in a universe of structure. Their immensity lies not in what they contain, but in their emptiness. To drift into such a region would be to leave behind the glow of galaxies and enter darkness, with only occasional faint light scattered across incomprehensible distances. The contrast between filament and void, presence and absence, gives the cosmic web its form. When we look at images of the web, it is tempting to see design. The branching threads, the clustering nodes, the vast symmetry. It looks deliberate, but it is the product of natural laws, of simple physics unfolding over time. The immensity does not require intention. It arises from gravity, expansion, and the seeds of quantum fluctuations stretched by cosmic inflation. The web is immense not only in size, but in the simplicity of its origin, a pattern that emerges inevitably when the universe is allowed to evolve. And yet, as immense as the cosmic web is, it too is bounded. What we can see of it is limited by the observable universe, the region from which light has had time to reach us since the beginning of the cosmos. Beyond that horizon, more filaments and voids almost certainly exist, but they are forever hidden from us, receding faster than light as space expands. The largest structure we can describe is limited, not by what exists, but by what we can see. Immensity becomes as much a question of perspective as of measurement. From Earth we can only see tiny slices of this web at once. A telescope captures a field of galaxies, each one a distant light, but it takes surveys across decades to piece together the larger picture. And even then, what we build are maps, reconstructions, models of what the universe looks like at scales so vast that no single human mind can hold them directly. the immensity of the web is not only spatial, it is cognitive, a challenge to imagination, a demand that we stretch our sense of scale to the breaking point. Perhaps the most humbling thought is that everything we know, every galaxy, every cluster, every filament, is only part of one cosmic web. The universe may be infinite. There may be other webs, other structures beyond what we can observe. Or perhaps the observable web is all there is, and its immensity is the limit. Either way, we're left with a picture of scale that dwarfs every earlier step. When we look at the cosmic web, it is the glowing filaments and the bright clusters that capture attention. They are the threads of light, the scaffolds of galaxies, the places where matter gathers and stars are born. But between those threads lie the voids, immense regions of space where almost nothing exists. If the filaments are the walls of the universe, the voids are its rooms, vast empty chambers stretching across hundreds of millions of light years. Their immensity lies not in what they contain, but in what they lack. A cosmic void is not entirely empty. There are still a few galaxies scattered within like solitary lanterns in a desert. There is still dark matter, thinly spread. But compared to the filaments, the density is so low that the impression is one of near nothingness. To drift into a void would be to leave behind the bright lights of galactic neighborhoods and enter a darkness where galaxies are rare, where distances stretch without comfort. Immensity here takes the form of emptiness, of silence on a cosmic scale. The Boötes void is one of the largest known. It lies about 700 million light-years away and spans nearly 330 million light-years across. Within that volume, astronomers have found only a few dozen galaxies where thousands would be expected. Imagine a bubble so vast that if our Milky Way were placed at its centre, we would not encounter another major galaxy for hundreds of millions of years of light travel. The scale is staggering. The Boötes void is sometimes called the Great Nothing, and the name feels appropriate. It is not a cluster of stars, not a filament of matter, but a gulf so large it becomes its own kind of presence. Voids are not mistakes in the universe's structure. They are part of the pattern. The cosmic web forms from matter flowing into denser regions, leaving behind under-dense areas. Gravity pulls material into filaments and nodes, and as it does, the spaces between grow emptier. Voids are the natural counterpart to clusters. Without them, the web would not exist. Their immensity defines the contrast, the negative space that makes the positive visible. Just as silence shapes music, emptiness shapes the universe's structure. To imagine what it would be like inside a void is difficult. On Earth, emptiness is never absolute. Even deserts have sand. Even the ocean has waves. Even the sky has clouds. But in a cosmic void, emptiness extends for hundreds of millions of light years. A galaxy drifting within one would have few neighbours. Its night sky would be darker, with fewer bright points nearby. The sense of isolation would be profound. For any beings that might evolve in such a galaxy, the universe might appear far lonelier than it does to us. They might look outward and see little, unaware that elsewhere the cosmos is dense with galaxies. Perspective, shaped by location, would redefine their sense of immensity. The largest voids rival the largest structures we know. Some span 500 million light-years or more. The KBC void, in which our own galaxy may reside near the edge, is estimated to be about 2 billion light-years across, though its boundaries are debated. If true, it would mean that our place in the cosmos is shaped not only by filaments and clusters, but by an immense emptiness as well. We live not at the centre of density, but on the edge of absence. That realization changes the way we think about our home. The immensity around us includes both presence and void. Voids also play a role in the expansion of the universe. Because they contain less matter, they expand faster than denser regions. Over billions of years, voids grow, pushing filaments farther apart. In this sense, emptiness is not passive, it is dynamic, shaping the future of the cosmic web. The universe's largest empty rooms are not still. They are swelling, stretching, influencing the shape of everything else. Their immensity is active as well as silent. There is something haunting about the thought of such vast emptiness. Human imagination gravitates toward fullness, toward stars, planets, galaxies, things we can picture and describe. Emptiness resists description. It is harder to hold in mind, harder to visualize, and yet the voids are larger than the structures. Most of the universe by volume is empty. The filaments are only the outlines. The true immensity lies in the hollows between. From Earth we cannot see voids directly. What we see are the galaxies, the glowing points. The emptiness is inferred, mapped by absence, charted by the spaces between lights. To map a void is to draw the shape of nothingness, to measure silence with rulers of light. It is an act of imagination as much as observation, because you are defining what is not there. The immensity of voids challenges not only our sense of size, but our sense of presence. They force us to consider that nothingness itself can be vast. And still, as immense as they are, voids belong to the same cosmic web as everything else. They are not outside the pattern. They are the negative spaces that make the pattern visible. To stand back far enough to see the web as a whole is to see filaments and voids together, equal partners in the architecture. The immensity of the universe is as much about what is missing as what is there. The great voids prepare us for the ultimate perspective. Beyond them lies not another scale of structure but the boundary of the observable universe itself, the horizon beyond which we cannot see, because light has not had time to reach us. The observable universe is not defined by clusters or filaments or voids, but by time, by the age of the cosmos, by the speed of light itself. It is the largest thing we can meaningfully describe, the ultimate room that holds all others. And within that room, the voids are the silent majority, the emptiness that gives form to the fullness, the immensity that is felt not by what it holds, but by what it does not. The largest thing we can talk about with certainty is not a cluster, not a supercluster, not even the cosmic web. It is the observable universe itself, the vast region of space from which light has had time to reach us since the beginning of cosmic history. Beyond it, space may stretch forever, but we cannot see farther because light from those regions has not yet arrived. The observable universe is therefore both immense and bounded, not by walls or edges, but by time. It is the horizon of visibility, the greatest scale we can measure, the stage upon which everything else plays out. The observable universe has a diameter of about 93 billion light-years. That number is astonishing. The universe is only about 13.8 billion years old, so one might expect that the maximum distance we could see would be 13.8 billion light-years. But space itself has expanded during that time, carrying galaxies farther away. Light that began its journey billions of years ago has been stretched by that expansion, and the regions it came from are now much farther away than they were when the journey began. The result is that the boundary of the observable universe lies nearly 46.5 billion light-years away in every direction. Multiply by 2, and you get the 93 billion light-year span that defines our cosmic horizon. Within that horizon are an estimated 2 trillion galaxies, each one containing billions of stars. The immensity of such a number is almost impossible to feel. 2 trillion galaxies, each a city of billions of suns, each sun potentially orbited by planets, some perhaps home to life. When you multiply possibilities across such scales, the imagination collapses under the weight. Even if only a fraction of those galaxies contain Earth-like planets, the sheer number suggests an abundance beyond reckoning. The observable universe is not only large, it is fertile, a landscape of possibilities as immense as the distances themselves. What we see when we look out at the edge of the observable universe is not galaxies as they are now, but galaxies as they were billions of years ago, because light takes time to travel. Looking outward is also looking backward. The most distant galaxies we can detect are seen as they were more than 13 billion years ago, when the universe was young. The cosmic horizon is therefore also a temporal horizon, a limit on how far back in time we can observe. Beyond it lies the unobservable, a realm hidden not by distance but by time itself. At the very edge of visibility lies the cosmic microwave background, the afterglow of the Big Bang. About 380,000 years after the universe began, the cosmos cooled enough for atoms to form and light to travel freely. That light has been stretched into microwaves by billions of years of expansion, but it still fills the sky in every direction. It is the oldest light we can see, a faint glow that maps the universe when it was less than 500,000 years old. Beyond that, the universe was opaque, a sea of plasma from which no light could escape. The cosmic microwave background is therefore the ultimate wall of observation, the farthest we can look, the true edge of the observable. The immensity of the observable universe challenges not just imagination but language. Numbers lose meaning. Billions of light years, trillions of galaxies, sextillions of stars. These words are accurate but abstract. What matters is the feeling they provoke, that we live inside something larger than comprehension, that every scale we thought was vast has been subsumed into something greater. The observable universe is not simply large. It is the largest thing we can currently describe, the container of all the other immensities. And yet, even here, we must remind ourselves that observable does not mean total. The universe may be much larger, perhaps infinite. We do not know. The observable universe is defined only by what we can see, not by what exists. Beyond the horizon, more galaxies almost certainly lie, more filaments, more voids, but they are receding faster than light, carried away by the expansion of space, forever hidden from us. The immensity we describe is both vast and limited, a paradox that defines our place in the cosmos. Consider again the diameter, 93 billion light-years. Imagine shrinking the solar system so that the distance from Earth to the Sun is only 1 millimeter. On that scale, the Milky Way would be about 100 meters across. The local group, about 1 kilometer. A supercluster, about 10. The observable universe on that same scale would stretch tens of thousands of kilometers, wrapping around the Earth many times over. That is one way to bring the number into a sense we can hold, though even then it strains our minds. Immensity here is not just size, but the stretching of our capacity to conceive size at all. What is striking about the observable universe is that it is centered on us, but not because we are special. Every point in the universe has its own observable horizon, centered on itself. From a galaxy billions of light years away, their observable universe would look similar, centered on them. Each observer has a sphere of visibility defined by light's travel time. The immensity is therefore universal, not personal. We're not at the center of the cosmos, but at the center of what we can see, just as every galaxy is. The horizon belongs to everyone. This horizon also shapes our questions. Because we cannot see beyond it, we cannot know whether the universe repeats, whether its structure is finite or infinite, whether our observable bubble is typical or unique. The largest thing we can describe is therefore also the most mysterious. Its immensity hides as much as it reveals. It is both an answer and a question, both a measure and a mystery. And when we think about our place within it, perspective shifts again. Earth, a small planet orbiting a modest star in a spiral arm of the Milky Way, within the local group, inside the Virgo supercluster, on the edge of Laniakea, inside the observable universe. Each layer dwarfs the one before it, until we arrive at the cosmic horizon, where everything we know is contained. The immensity of the observable universe is not only a measure of size, it is a reminder of belonging. We are inside this structure, inseparable from it, threads woven into its fabric. And still the story of size is not finished, because even within the observable universe, structures exist that stretch imagination further, and beyond the horizon, perhaps something larger still waits, unseen, forever beyond reach. The observable universe is immense, but it may not be ultimate. It is our horizon, not the universe's. The observable universe defines the largest horizon we can measure, a sphere nearly 93 billion light-years across, filled with hundreds of billions of galaxies, each galaxy a city of billions of stars. And yet, even as we describe it, we know it is not the whole story. The observable universe is not the universe itself. It is only the part we can see. Beyond that horizon, more space exists. What it contains and how far it stretches remain among the greatest questions in science. The immensity we know may only be the beginning of something larger still. The first and simplest speculation is that the universe extends far beyond the observable, perhaps infinitely. If that is true, then what we can see is only a bubble within an endless expanse. A horizon is like the circle of ocean you can view from the deck of a ship. It feels like an edge, but it is only a limit of sight. Sail far enough and more horizon appears, endlessly repeating. If the universe is infinite, then every direction continues forever, with no boundary, no wall, no outside. Infinity is difficult to hold in the mind, but it is a possibility that science must take seriously. If the universe is infinite, it raises strange implications. Within infinity, every possible arrangement of matter must occur. That would mean that far beyond our observable horizon, there are galaxies identical to ours, stars identical to the Sun, planets identical to Earth, perhaps even copies of you listening to this very thought. Not because of magic, but because infinity requires repetition. In an endless space, patterns recur. The immensity of infinity is not just in its size, but in its consequences, the idea that existence might repeat itself across unreachable distances. Another speculation is that the universe, while vast, is finite but unbounded. That means it has no edge, but it loops back on itself, like the surface of a sphere. On Earth, if you walk far enough in one direction, you eventually return to where you started. In a finite but unbounded universe, travelling in a straight line far enough might eventually bring you back to your starting point, though on scales so large that no journey could ever achieve it. The immensity in this case is not infinite distance, but endless return, the paradox of a space without edges, yet without infinity. Some theories suggest that our universe is only one bubble in a multiverse. In this view, our observable universe is a patch of a much larger reality, one bubble among countless others, each with its own laws of physics, its own constants, its own possibilities. These bubbles might never touch, or they might occasionally collide, leaving imprints in the cosmic microwave background. If such a multiverse exists, then the largest thing is not the observable universe, but the multiverse itself, a sea of universes beyond universes. Immensity here becomes layered, stacked, a hierarchy of realities. There are also ideas from cosmology that suggest our universe might be embedded in higher dimensions. Just as a two-dimensional sheet can exist within three-dimensional space, our three-dimensional universe might be a surface within a higher dimensional reality. If so, then what we see as immense might only be a slice of something larger, a shadow of a structure beyond our senses. Immensity here becomes not only about distance, but about dimensions, an expansion of what it means to exist at all. Even within the observable universe, we encounter structures that challenge the limits of theory. Some walls and alignments of galaxies stretch so far that they seem to contradict the principle of cosmic homogeneity. The idea that on the larger scales the universe should be smooth. If these structures are real, they may hint that our understanding of size itself needs revision. Perhaps the universe is larger, more connected, more patterned than we can currently explain. The immensity we think we know may be incomplete. Speculation also reaches into time. The observable universe is bounded by the age of the cosmos, about 13.8 billion years. But what came before? Did the universe have a beginning, or has it existed forever in some form? Some theories suggest cycles of expansion and contraction, universes born and reborn across infinite time. Others propose that time itself began with the Big Bang, and asking what came before is meaningless. In either case, immensity is not only spatial, but temporal, stretching backward and forward in ways we cannot fully imagine. And then, there is the question of whether space truly ends at all. Expansion continues, carrying galaxies away from us faster than light as they cross the cosmic horizon. These galaxies still exist, but they are no longer visible, their light forever beyond reach. If space continues to expand indefinitely, more and more of the universe will slip beyond sight, leaving us in a future where only our local group remains visible. The immensity will still exist, but it will be hidden. Our horizon will shrink even as the universe grows. Speculating about what lies beyond is not only scientific, it is also human. We are creatures who look outward and wonder what is past the horizon. Sailors once looked at oceans, explorers looked at maps, and always the question was, what lies beyond? The cosmos offers the same mystery. Scaled up to the ultimate level, the immensity of the observable universe does not end the story. It opens the door to questions that may never be answered, but that shape the way we think about existence. Whether the universe is infinite or finite, whether it loops or stretches forever, whether it is one bubble among many or the only one, each possibility expands our sense of what is large. Each one redefines the idea of immensity. The largest thing in the universe may not even be in the universe at all, but the universe itself, and perhaps even something beyond it. And yet, there is something grounding in remembering where we began. From the scale of mountains and oceans to the size of planets, from stars to galaxies, from clusters to superclusters, we have stepped outward again and again, each time finding something larger. Now, at the edge of the observable, we are faced not with an answer, but with possibilities. Perhaps the immensity is infinite, perhaps it is cyclical, perhaps it is layered in ways we cannot yet imagine. The scale of speculation is itself a kind of immensity, larger than measurement, larger than proof. We have travelled outward step by step, beginning with the familiar, expanding into the unimaginable. Mountains, oceans, planets, stars, galaxies, clusters, webs, voids, horizons. Each step redefined size. Each comparison stretched our sense of scale further. And now we arrive at the end of the journey. Not because the ladder of immensity has reached a final rung, but because we as humans can only climb so far before the numbers become more than numbers, before distances dissolve into abstraction. The universe may be infinite or layered beyond comprehension, but our hearts and minds remain finite. The closing question is not what the largest thing is, but how we, as small beings on a small world, hold this vastness at all. When you think about the larger structures, it is easy to feel insignificant. Earth, which holds every story, every life, every memory, is smaller than a grain of dust in comparison to a galaxy. The sun, which feels overwhelming in its power, is modest beside a red supergiant. The Milky Way, with its billions of stars, is just one galaxy among billions, and even the observable universe, immense beyond description, may itself be only a fragment of something larger. If size alone defined meaning, then our place would seem trivial, erased by immensity. But meaning does not work that way. Our sense of significance is not measured in light years. It is measured in presence, in awareness, in the ability to look outward and wonder. The fact that we can contemplate these scales at all is extraordinary. A brain, weighing a little over a kilogram, a fragile network of neurons, can imagine distances measured in billions of light years. A creature that evolved to walk on plains and climb trees can map galaxies and speculate about infinity. That capacity is its own kind of immensity. We are small in body but vast in thought. The universe may be larger than us, but through curiosity we reach across it. Holding that paradox, our smallness and our vastness, is part of what it means to be human. There is also comfort in scale. The universe does not diminish us, it situates us. Just as a single drop belongs to an ocean, we belong to this cosmos. Our atoms were forged in stars, scattered by supernovae, gathered into Earth. We are not separate from immensity, we are made of it. Every breath of oxygen, every trace of iron in your blood, every calcium in your bones, was once part of something larger, part of stars and clouds and galaxies. Holding the vastness is not only about imagination, it is about recognition, about remembering that immensity is inside us as much as outside. When we look at the night sky, most of what we see is history, light that has travelled for years, centuries, millennia, before arriving at our eyes. Every star is a message from the past, every galaxy a postcard from billions of years ago. To know this is to feel time as well as space, to realise that we live surrounded not just by distances, but by ages. Holding the vastness means holding time. feeling that our moment is brief but connected to a chain of moments stretching back to the beginning. It is humbling, but it is also grounding. We are here now, in a universe that has been unfolding for nearly 14 billion years, and we are part of that story. It is also worth remembering that vastness and intimacy are not opposites. You can stand at the edge of an ocean and feel both the immensity of water stretching to the horizon and the intimacy of sand between your toes. The cosmos works the same way. You can think about galaxies spanning hundreds of thousands of light years and still feel the warmth of the sun on your skin. You can imagine clusters of galaxies colliding and still notice the flicker of a candle in a quiet room. Holding vastness in a human heart does not mean abandoning the small. It means seeing both scales at once, the grand and the close, the infinite and the immediate, woven together. There is a quiet reassurance in knowing that the universe does not require us to understand it in order to continue. Stars burn, galaxies turn, clusters evolve, webs stretch, voids expand, horizons recede, all without our permission or awareness. We are free then to engage with it, not as masters, but as participants, to wonder without needing control, to admire without needing ownership. Holding the vastness is not about conquering it. It is about resting within it, about recognizing that belonging is enough. And when you bring all the scales together, Earth's mountains and oceans, the planets of the solar system, the giants of the stars, the spirals of galaxies, the swarms of clusters, the filaments of the cosmic web, the voids, the horizon, you see that the universe is not only immense but layered. Each level of size builds on the one before it, each one a perspective that reshapes the meaning of the last. Holding vastness in a human heart means remembering that no single scale cancels another. The small is still meaningful within the large. The personal is still real within the cosmic. The immensity of the universe can inspire awe, but awe is not the same as fear. Awe is the widening of perspective, the expansion of what we thought possible. It is the recognition that there is more, always more, than we can see or know. To hold vastness in a human heart is to carry awe gently, not as a weight, but as a light, as a reminder that we live inside something greater than we can imagine. That awareness can be calming. It puts our worries, our anxieties, into perspective. Against the backdrop of billions of light years, a single day's troubles shrink, not because they are unimportant, but because they are part of a larger context, part of a universe that endures. As you think of the largest things, the galaxies, the webs, the horizons, remember also the smallest, the cells in your body, the atoms in those cells, the particles that dance within those atoms. Vastness exists in both directions. The universe stretches outward to billions of light years, and inward to subatomic scales. Both are immense in their own way, both beyond our everyday senses, both requiring imagination to hold. To keep vastness in a human heart is to accept that size is relative, that meaning exists across scales, that we belong in the middle, bridging the small and the large. And perhaps that is the most human response to immensity. Not to solve it, not to measure it fully, but to live alongside it, to let it deepen our sense of place. The largest thing in the universe may be beyond our reach, but the wonder of it is not. Wonder is always available in a night sky, in a photograph of a galaxy, in the thought of a light beam travelling for billions of years to arrive here now, to meet your eyes. That wonder is the way vastness enters the heart, not as numbers, but as presence. So as we end this journey, consider once more the question we began with. What is the largest thing in the universe? The answer depends on where you stop climbing the ladder of size. A mountain, a planet, a star, a galaxy, a cluster, a supercluster, a filament, a horizon. Each is the largest thing until you step outward again, and beyond each step lies another. The truest answer perhaps is that the largest thing is always the next thing, always what lies just beyond our current sight. And holding that thought, that there is always more, may be the best way to hold vastness in a human heart. And so, here we are, At the quiet end of the journey, we've drifted together from the smallest comparisons we can hold in hand to the larger structures the universe allows us to glimpse. Along the way, size has grown and grown, each step revealing something larger than what came before. And still the mystery lingers, because there is always more beyond the horizon. If you found comfort in these thoughts, in letting your mind stretch into spaces larger than words, you're welcome to return here any time. This is a place where wonder and rest belong together, where curiosity can be gentle, where the vastness of the universe becomes a backdrop for quiet. Now, let the thought of galaxies and horizons drift softly into the background. Let your breathing slow, your body rest, your eyes grow heavy. You are small in the universe, but you are not lost. You belong within it, as much a part of its immensity as the stars themselves. Good night.